Good morning. As I mentioned earlier, I was going to give you the presentation this morning for the class that starts at 5:15. And I was going to give this to you via video because I'm giving a separate presentation, and unfortunately this other presentation happened to overlap, and I did not know that when I committed myself. But in any case, I hope that you will have the opportunity to listen to this video. And if not, then you can come in person in the lecture that I have with the other section that starts at 3. In any case, what I wanted to do today here is to go briefly through the introduction of the dielectric boundary conditions. In fact, the air dielectric is a special case of that, where one of the dielectrics is air, but we are going to look at the more general case. I would like to cover those boundary conditions to remind you, since we introduced them last time. And then what I would like to do afterwards is to implement those in 3 examples of capacitors. So that's going to be the lecture today, and that's going to be the end of electrostatics. And on Wednesday, we'll start with magnetostatics. So as we mentioned, here is a dielectric interface. And in fact, as you can see from here, let me in fact use my laptop. Okay. Apologize for that interruption, but I needed to use my pen. So here, as you can see, we have well, I have some problems, all kinds of problems today. All right. So this one is dielectric 1, and this one is dielectric 2. And what we've mentioned is that if we take one point on an air dielectric interface, D at that point will, in the most general case, has a particular direction that is shown here. And it's, you can see it, I'm trying to outline it. And then, as a matter of fact, what I will try to do is to move it into the initial location. And then we split this component of this vector into 2 components, the normal component to the interface, which is this one, at this point at the center, and then the tangential component, which is this one. And we do the same thing for D at that point on the interface. This is the point on the interface. Now, we did it for D2, which is just above the interface at that point. We split it into components, and now we split D1, which is also at that base, a point on the interface, but just below it. So it is in medium 1. So blue is medium 2, pink is medium 1. And we split therefore D, which at that point on the interface, it is possible that it's going to have 2 different directions. All right, it's going to be continuous, obviously, but the direction of the D changes as it moves from one point to another. And then here it shows how it changes just before the point and then after the point. And so what we have is, according to the boundary conditions, as we call them, for the dielectric interface, first of all, these are some definitions that I have about D1, which is the flux density at one point on the interface just inside medium 1. D2, which is the flux density at the same point on the interface, but just above it. So it's medium 2. And then how we characterize the two media 1 and 2 by two scalars. One is the electric permittivity, we usually call it permittivity, and it's equal to the relative dielectric constant times the permittivity of the free space. And then is the permeability or magnetic permeability, we call permeability. And for dielectric materials, this is always equal to the permeability of free space. And then we do this, we use these constants, epsilon1 and epsilon2 for the two media. So according to the boundary conditions at that point on the interface, which is here, we have continuity of the normal component of the electric flux density, and then we have continuity of the tangential component of the electric field intensity. Now, you need to remember that differentiation that is on a dielectric interface, you have continuity of the normal D, and you have continuity of the tangential E. So this is important. Now, what are we gonna do next is to take these conditions and apply them in the case of a capacitor that is filled with different dielectrics. But before we do that, we are going to remember the fundamental equations for a capacitor that is filled only with one dielectric. So we have here two conductors, the blue one, conductor 1, and then conductor 2. And we assume that they behave like infinite planar conductors. However, they have a given area. Their area is not infinite. What we mean by saying that they behave as infinite conductors is that we assume that we don't have edge effects, as I discussed in class. We assume that always the field is not going to be impacted by the terminations of the conductors. And what does that really mean? It means that always the field inside this capacitor, which we call ideal because it does not have edge effects, will always be, the lines will be parallel to each other and then will be perpendicular to the two conductors, always. So here is, in fact, is my drawing, but all of these lines are perpendicular to the conductors, to the two conductors. So for a capacitor to fulfill these requirements, to be an ideal, in other words, to not have edge effects, we need to have that the separation between the two conductors is so much smaller than the size of the two conductors, like whatever size of it is. So if D is very, very small compared to both sizes, I mean, a conductor is going to probably be most of the time rectangular. And therefore, D has to be much smaller than both sides of the rectangle. If it's circular, it is possible to have a circular conductor, then it has to be much smaller than the radius. But these are the two possibilities for the shape of the conductors. In any case, so when that applies, we have now, in most cases, in all cases rather, we have that a conductor is separated from the other conductor in a capacitor by a dielectric. Otherwise, how are you going to keep them apart at a particular distance D? All right, they will collapse if we don't have something to separate them. So we always use a dielectric D. And then now, in addition, as we will see later, the dielectric is not only used to separate the two metals, but is also used to increase the capacitance. And that's what we're going to see from the equations before. So what we are doing first is that we write down the things that we have already seen. And what are those? First of all, what we have seen is that D in this is going to have only the normal component on the conductor because, as we said, there is no field inside the conductor. There is no electric field. Therefore, there's no electric flux density inside the conductor. The field inside the conductor is zero. And as a result, the electric flux density inside the conductor is zero. If the field inside the conductor is zero, that and the electric flux density are both zero, that implies that there is no tangential component on the conductor of either one of those. Therefore, both D and E will have, in the case of an ideal capacitor, and in any case when you have a metal, on the surface of the metal, there is going to be no component of E or D, and it's only the normal component. So always, as we've said before, the electric field initiates on a metal surface and is always perpendicular. But here, in the ideal capacitor, when the separation is so much smaller than the size of the capacitor, we also found that the electric field is going to be continuous through that and constant. So D and therefore E have only the normal component. And also we found that D is going to be equal to the charge density on the surface of the conductor. And here the way we have connected the conductor to a battery, you can see that the charge density you're going to have on the lower surface of the upper conductor is going to be positive. And those positive charges will attract negative electrons on the top surface of the lower conductor. And therefore, the electric field lines will start on the positive charges and will end on the negative charges. And we also found, as I said, looking at module 9, that D is equal to Q sub S, but Q sub S is the surface charge density, and therefore, since in an ideal conductor is uniform, then the surface charge density is equal to Q, total Q, divided by the area. All right, so we have that in equation 2. And therefore, from the above, we have the D sub X inside, of course, the dielectric is equal to epsilon E sub X. Epsilon is the dielectric permittivity for the dielectric, which is equal to epsilon sub r, epsilon naught. Epsilon sub r is the relative dielectric constant. Epsilon naught is the free space permittivity. And of course, the value of the electric field. And therefore, from here, we find the electric field is given by that. All right. Also, we know from module 9 that inside an ideal capacitor, the voltage that applies across the two conductors is equal to the electric field, which is constant and normal to the conductors, times the distance. And now, having 5 in mind, then we introduce the concept of a capacitance, and also we introduce the expressions that we found before, and then we have from here that a capacitor in an ideal the capacitance of an ideal capacitor is equal to epsilon sub r, which is the relative dielectric constant, epsilon naught, which is the permittivity of free space, times the area of the conductors divided by the distance. And from equation 6, it's just a simple rewrite of the previous. We can see that there are 2 types of parameters that they impact the capacitance. And usually when we try to create a capacitor, the capacitance, we want to have the capacitors relatively large compared to the parasitic capacitances, all right, that you have in your structures. So we would like to have an increased capacitance, and then therefore either we increase epsilon sub r, or we increase the ratio of A over D, which means the following. We always need, which is true in an ideal capacitor, to have the area much larger than D. So we try to maximize that ratio. And in addition, we try to maximize epsilon sub r. And there, the combination of the two gives us the desired C. Sometimes in microelectronics, your D may be specified. or your A cannot be bigger than something, and your D cannot be smaller than something. In that case, you have to play with the three components, epsilon sub r, A, and D. And that is a design problem. All right, whenever you have to select between parameters, multiple parameters, to achieve a specific goal, and here the specific goal will be the value of the capacitor, of the capacitance rather, then you try to design it using the appropriate constraints. All right, so now having remembered the characteristics of an ideal capacitor, we are going to the case where our capacitor is not filled by one single dielectric, but by two. And sometimes that is appropriate when in microelectronics, for example, your capacitor may have two different oxides, all right? One could be silicon oxide, the other could be silicon nitride. And then those two will be determined by the fabrication of your circuit. And then you use two conducting plates, you want to calculate the capacitance, might be a desired capacitance, might be a parasitic capacitance if there is just an overlap. But in the desired capacitance, obviously, as we discussed right now, you're going to have two different media, because silicon oxide and silicon nitride, they have two different dielectric constants. So of course, in that case, you will have to use a different formula from the previous one to characterize the capacitance. And that's what we are going to try to learn. All right, so here I give you the two different materials, epsilon R1 and epsilon R2 are the two relative dielectric constants. D1 and D2 are the thicknesses of the two materials. And then now, again, we need to remember what happens in an ideal capacitor. First of all, D, and therefore D1 and D2 are much smaller than the area of the conductor. Therefore, there are no edge effects. Second, D and E will continue to be perpendicular to the conductors. The fact that we have two layered dielectrics is not going to change that. And especially because the dielectrics are layered along the direction of the conducting surfaces, as we always do. And then now we write D and E. We write D and E. And then from here, now we remember the boundary conditions. What are the dielectric boundary conditions are telling us? That the normal component of the electric flux density is continuous. They also say that the tangential component of the electric field intensity is continuous, but we don't have a tangential component here. We only have normal components to the interface and to the conductors. Therefore, we are using this property. All right. So I'm writing as part of equation 8, and it's true for all along the interface. So now, what is the other thing that we have? That the surface charge depends on the total charge and the area. And the voltage here is responsible for how much charge goes to each conductor, plus Q on the upper conductor, minus Q on the other lower conductor, which implies that the charge density on the upper conductor is going to be positive, on the lower conductor is going to be negative, and they are equal, but with an opposite sign, as it shows there. So that's also what is expressed in equation 9. Now, what we know is the total capacitance for this structure, which is two conductors to dielectrics, is going to be the ratio of the total Q that is delivered by the source divided by the voltage. And how much is the total Q? QS A over V here. So total Q is QS times A over V gives the total capacitance. And then now we want to find V. But V in this case is going to be different from V before. It's not the V, the V that we have to find is not going to be E times D as we did before, because now we have two different dielectrics. And therefore, we have to write the expression for voltage like here. And then from that relationship, which we know, that the E is the gradient of V, negative gradient of V, we find this expression here. So now you see that V is expressed differently in terms of dielectric, the electric flux density and D1 and D2, epsilon 1 and epsilon 2. So if we take that expression and we put it in the capacitance expression, and we work on that, what do we find? We find that if we were to consider its dielectric on its own with a capacitor as being a separate capacitor, as if, for example, we would place a metal somewhere here, all right? But a floating metal. Let's assume that we place a floating metal there. So each part of this capacitor, if that were to act as a separate capacitor, then practically what that tells you is you would have these two capacitors in parallel, in series. So you will have one capacitor here and one capacitor there, and you will have these two capacitors in series. So if you have two capacitors in series, then the total capacitance is going to be given by that, all right, and is expressed in this form, where each one of these capacitors is considered to be an ideal capacitor and they're connected like in series, even if there is no metal in between. There's no metal between the two dielectrics, but as it seems like it works as if there was a metal. Because even if you introduce a metal, the result is going to be the same. If you put a metal in between the two interfaces, which is not connected to anything, a floating metal, is going to work as if there were no metal there. And it's going to give you this capacitance. It's going to give you total capacitance, which is the result of two capacitors in series. Now, we're going to the other case where we have a capacitor, but with two types of materials, all right? And the materials are side by side. So they share the same upper conductor, they share the same lower conductor. In that case, again, we define two separate fields, two separate electric flux densities, since the materials are different. Now, in this case, since the fields continue to be normal to the conductors, on the interface, the fields here will be parallel. And then what we know about the the electric boundary conditions, we know that the fields there, which are tangential, the electric fields will have to be continuous. That's from the boundary condition. And therefore, we write that, and this is the condition on the interface. But since the electric fields are equal in each region, and therefore they are continuous through the interface, that implies that the electric field is constant throughout the whole area. And since the field is constant, then the electric flux density is not, because the electric flux density in each region is connected with the field through a scalar, the electric permittivity, which is different for this medium and different for that, from that. So the electric fields are constant throughout the whole region, despite the dielectrics, but the electric flux density changes from the pink to the green area. Also, there is a change in the total charge. So the total charge now, we consider it to be the the charge density on its conductor multiplied by the area. So we have the charge density multiplied by the area and the sum of these two. So the density here multiplied by this area gives one charge Q1. The density here multiplied by this area gives another charge Q2. And the sum of the two charges is the total charge. And then from here, we find the following relationship. We find, if you follow this, that if you consider this one as one capacitor, and this one as a second capacitor. Since the two capacitors share the same two conductors, they are in parallel, and therefore the total capacitance here is going to be the sum of the two. So the previous case where the dielectrics were horizontally placed next to each other, the capacitance is in series. And in this case, where the dielectrics are side by side, the capacitance vertically parallel, the capacitance is in parallel and therefore is the sum. Now we have another example where the ideal capacitor is filled with multiple dielectrics. And in this case, without doing what we've done before, we will assume that everything that we have seen so far applies. So first of all, we will, from the most recent of the two examples, we will assume that this is one capacitor and this is another. Okay, if we assume that, then this capacitor here, who has area A1, and this capacitor here, we know there will be in parallel. Therefore, I'm writing here. But this capacitor here has two materials, horizontally placed, side by side, which means that on the left, the capacitor is going to be the result of two capacitances in series. So one is going to be this capacitance and the other is going to be this capacitance. So first of all, we find this capacitor here as the series combination of two capacitances. And then, so we find that here, excuse me. And then we sum to this the capacitance from this side. And therefore, we have the total capacitance to be like this form. And therefore, we have the total capacitance to be here. So you can think of multiple combinations of materials, but I would say these three are the most reasonable. You're not going to see anything different than that. So we need to keep this in mind. The last thing that I wanted to do is using everything that we've learned so far to think of this problem. And this problem I will, if we have time in class, because I would like to make some comments about the midterm. If we have time in class, we are gonna do it together. But if I don't do it together, I will probably given it to you as a quiz. So I will give you this problem and I will give you different options of what the capacitance of this is between A and B, all right, as I'm asking. If we have time, we'll do it together in class. If not, I will give it to you as a quiz. All right, but in this case, you need to remember the following. If you have conductors that are not fully overlapping to make like a capacitor that we have seen, but they are overlapping and this distance D1 and D3 is much smaller than the overlap area, then this section here operates like a capacitor, and this section here operates as a capacitor. Also, this one here, this conductor has the same potential, and all of this conductor has the same potential. If D1 and if epsilon 3 and epsilon, epsilon sub r and epsilon sub r in that case is very, very high, then practically you can assume that most of the charges will be here and very few charges will be there. But in reality, also you can assume that there is going to be one capacitor here, one capacitor there, and a third capacitor here in free space. And then you will have to find the capacitance, total capacitance between A and B. So we are going to do this in class. but I would like you to think of where the charges will go and whether this is going to have any charges that are substantial, or whether most of the charges will be here, and then fewer charges will be here to face each other. So that's where we have to think about it. But I will try to do it in class. If not, I will give it to you as a quiz, and then you have to think on exactly how this charge distribution is going to apply. In any case, I hope that I can do it in class. And if I do, even if I will not cover it here because I have 5 more minutes that I need, or like 10 more minutes, but I need to speak of the midterm for a second. If I don't have time to do that, then I will give you the quiz on Wednesday, and I will do some discussion of this problem before I give you the quiz, just to help you with the distribution of the charges. All right, so after this, what I would like to do next is to go to the quiz. One second. I hope I can. Yes. I've graded the quiz, but I would like to go to a homework that I gave you and explain what this homework is. So we'll go here. We'll go assignments. Here. Let's go and look what will be homework for, but it's not gonna work as a homework. This is gonna have 250 points, as you can see, first of all. You see the points there, and then I would like you to read everything. Well, that is supposed to be 3, but look at the final in red that says your grade from this assignment will be averaged with your individual midterm grade. And then that is going to be your final grade for the midterm. It's going to get 250 points, but that's an opportunity for you to improve your grade for the midterm. So how I graded the midterm, there's a great deal of people who got 200 and above. And even for those who got 250, what I graded was your understanding of the problem and whether you knew exactly how to approach it, and my understanding of whether you would be able to find the correct solution had I given you enough time. I did not check the final numbers, but I checked your approach. So that is how I gave 200 to 250. 250 were those who had a perfect approach, and maybe they were very close in the final solution or almost there. And anybody before 250, they had some glitches in their approach that could have become an issue. Those between 100 and 200, they had some understanding of a problem, of the problems rather, but given enough time, they would have done a good portion of the meter. And then those who had below 100, they had such a limited understanding of the problem that no matter how much time I would have given them, they would not be able to solve it. So what I would like you to do as part of this assignment is I want you to put together a very thorough and well-written solution for each problem. At the end of each problem, after you finish the solution, I want you clearly to say, this is the if you were especially below 100 or below 200, to say, this was my misunderstanding, which now I have corrected, and explain what your misunderstanding was before, and now how you have corrected it. I mean, as an essay, not a very long essay, but I want you to internalize yourselves of what your misconception of the problem was before. This is extremely important to do in everything we do in our life. We have ourselves to do some self-reflection. And that is, I ask you to do that just so I make sure that you have gone through this process. And also at the end of your solutions, I would like you to attach your individual midterm exam solutions the way you have assigned them, so that I don't go back and forth. It's gonna be easier for me to have everything in front of me when I grade it, because I will grade this myself. Okay. Now, what I found from this grading was that the students who were below 100 were the students who do not normally come to class. They had no idea or recollection of what I had discussed in class and how charges distribute on conductors. They were trying to solve every problem using Coulomb's law. That says that they were not coming to class, as we normally know. As we all know, those of us who come to class, we know that 50% of the class does not show up. That is true for both sections. And they try to solve the midterm. The one message that I would like to give all of you is there is no way you can pass this class by not coming to class. I don't know how to say that. This is one of the most difficult, conceptually speaking, classes in electrical engineering. We are trying to, at least I try to make it as physics-based, so you can connect with the things that you've learned before. And I'm trying to limit the equations and remove integrations, so you don't lose yourself in the math. And in the process, you forget the physics. I personally believe that if you understand the physics, you will be able to solve very complex problems fairly accurately. So, having said that, I cannot claim that with these simplifications in the presentation of the material, you will be able to pass this class by reading my notes, by reading any book, by using any source on the web, or by getting advice from colleagues, friends, or others, tutors who may help you. You are not going to be able to pass the class. So my advice will be, now that it's still early, we are not even in the middle of the semester, please come to lectures. And that is my biggest advice that I can give. I have sent the people who are below 100, I've sent them individual emails to come and speak with me. I would like each one of them to come and speak with me. So we have a discussion. I need to understand what the issues are. Is it something I can fix in the class? Is there something in the class that would help you come that I could do other than not giving the class, obviously? In any case, I would like to know. So that's why please make sure that you come and see me at an appropriate time. The other thing that I wanted to say is that came to my attention that a few people copied each other. I believe I said that to everyone, I said that you should not work together. This is an individual exam. And I also mentioned that I'm not a police person to go around and trying to police you as you take the exam. However, neither I would be the one to try to investigate who has copied or not each other. However, if it comes to my attention, then I will have to act on it. So I've noticed it's not an extensive issue, but it has happened. And I need to think about how to deal with this. So I just have to tell you, for those who hear, who listen to this, and then who may be done this, to know that I will follow up. In any case, with all of this, I still have to say that those who got above 200 is a very large number. So obviously, coming to class and reading the lectures and practicing pays off. And I hope that with this one, you're going to also pay attention to the details. And I hope that this is going to improve your grade. So with that, I would like to finish. I would like to encourage you to come to office hours if you have any questions, or email me individually and meet with me. Again, thank you. I apologize for not being able to be here in person today, at least for the one section, but I will be in the next section. And if you have any questions, or if you want to hear my presentation live, please come. Thank you.